Today's video is on precipitation reactions and net ionic equations. Precipitation reactions are, if you remember from our previous notes, all examples of double replacement reactions. So that's what we're going to see today, and we're going to learn some rules about how to predict what's going to form a solid. So what does it really mean when a compound is aqueous? So if I take, for instance, here solid sodium chloride and I put that into water, what actually happens? Well, it doesn't exist as NaCl anymore. What we get is actually separate sodium and chloride ions. And even if we wrote this as NaCl aqueous, we would know that this actually doesn't really exist like that. It exists totally separated. It's as separate sodium ions and chloride ions. So kind of what you would see down here in this picture, if I took, for instance, salt and put it into water, I'd end up with separate sodium ions and chloride ions. They've come apart. They don't exist as one unit anymore. Okay, so the compound really exists as ions in water. It doesn't exist as NaCl anymore, but as sodium and chloride ions. Kind of an important thing to remember here is, for each one that dissolves, like in sodium chloride, I got one sodium and one chlorine, one chloride ion. But if for something like calcium chloride, which is also a solid, it's an ionic solid, you put that into water, well, for every one calcium ion that now we say dissociates, which means comes apart, for every one calcium ion that dissociates, you get two chloride ions. So it'd be important to have these examples in your notes explaining what happens when you actually put a soluble, meaning it can't dissolve, a soluble salt into water. What we get are the ions. So just kind of, you don't have to write this down, but types of reactions in aqueous solutions. Today what we are looking at is precipitates, which is the formation of a solid from two aqueous solutions. Next unit, we'll talk about acids and bases, and those reactions will be double replacement reactions because they will be happening in water, and they'll be forming two products, so we're going to have that in Unit 7. And then we have formation of gas, which is what we talk about with gas laws in Unit 8. Okay, so precipitate, just as a definition, you've seen this now a few times, but in case you haven't gotten it down at this point, a solid formed by the addition of two solutions. Okay, so in order to identify it, I have two aqueous reactants, and one of my products is a solid. The other one's going to be aqueous. Doesn't matter which position it's in here, but only one of the products is a solid, the other one is aqueous. And these are always the result of a double replacement reaction. So my example here, AgNO3, aqueous, so aqueous silver nitrate plus aqueous sodium chloride. Okay, we get aqueous sodium nitrate over here and solid silver chloride right here. This is a precipitate, right? This is your precipitate, okay? Now, you may be wondering, well, how did I know that this was a solid and this was aqueous? And those are the rules that we're going to get here in a few minutes. But the solid is the precipitate, so that's what I need you to be able to identify. Okay, so using that same idea right here is this equation, 2 sodium hydroxide, which is aqueous, plus 1 aqueous copper 2 chloride, yielding 2 aqueous sodium chloride and solid copper 2 hydroxide. Okay, so this is the reaction we're going to look at. This one being our precipitate, the CuOH2, right, which is a solid. So, remember, ionic compounds exist as ions in solution. So before any of these products form, right, if I were just to have these things floating around in solution, so ignore all that for a moment over here on the right, but just these two things. What I really have is this broken up. I've got really sodium ions and hydroxide ions, I guess 2 for each of these. And I have 1 copper ion with a +2 charge, and then I've got 2 chloride ions from that Cl2 there. So all of that's floating around in solution. It's all aqueous. Okay, and that's what's going on right here. I know it's kind of messy, but you get the idea. I've got a bunch of aqueous things floating around. Okay, and then over here on this side, NaCl, well, that's still 2 aqueous sodium ions and 2 aqueous chloride ions. Those are still separated because they are aqueous. This one over here, though, all right, your precipitate does not exist as ions in solution anymore. Okay, this stays together. Right, it's now bound together. It's not floating around in the solution anymore. Okay, so it's now one thing. So if we look at this whole thing here and take all the ions into consideration and then keep the precipitate together, okay, we call this the complete ionic equation. Okay, complete ionic equation. Every single ion involved in that reaction is listed out. And I've kind of drawn what's going on down here. 2 sodium hydroxides, right, which is solid. If you put that into water, right, you're going to get 2 of each ion floating around. And 1 CuCl2, I'll get 1 copper ion and 2 chloride ions. Once all of these are in the same solution and you allow it to react, here's what happens. Your sodium and chloride ions are still floating around in solution right there. And then the solid that forms, that CuOH2, okay, that's not floating around in solution anymore. It's a solid that shows up on the bottom. Or it may look kind of murky, but it'll settle out. CuOH2, which is a solid, is now what's down there on the bottom. So, complete ionic equation's got all the ions in it and keeps the precipitate together. One thing to notice here with all these ions, it's kind of messy, it's long, and so as chemists we like to try to reduce the size of this equation. But what do you notice about the sodium and chloride ions? Well, it's sodium ions right here, I've got chloride ions right here, I've got more sodium ions there, more chloride ions there. I have them present on both sides of the arrow. I've got 2 sodium ions on the left and 2 on the right, 2 chlorides on the left, 2 chlorides on the right. And if you notice, then that means as the reaction has happened, actually nothing happened to the sodium ions. Nothing happened to the chloride ions. They just stayed there. They didn't actually react. They're not really a part of this reaction. Yes, they're there in solution. They're still present, but they never actually did anything. So we have a name for these ions after you write out a complete ionic equation. We call these spectator ions. Okay? They do not participate in the reaction. So in order to identify them, it's just any ion that's in both the reactant and product side that just never reacted. That's a spectator ion. So what we want to do is remove those from the complete ionic equation because they're not actually reacting. So once we've identified them, go ahead and circle them again here. We can just cross them off because they are not going to participate. And then what we're left with is the actual reaction. I'm left with 2 hydroxide ions here. I'm left with a copper 2 ion. These are both still aqueous. And then over here, what's left, the only thing left on my product side is actually just my precipitate. Okay, the solid. And what we've done by removing spectator ions is we've now written a net ionic equation. Okay, so it's removing the things that don't actually react, and it's called the net ionic equation. It's really easy, actually, kind of the shortcut to this one, instead of having to necessarily write out every single spectator ion and canceling it every single time you have a question. Once you've identified what the precipitate is going to be, which you'll get the rules here again in just a moment, but once you've identified which one's the solid and which one's your aqueous product, if you put that over on the product side of your net ionic equation, your precipitate's the only thing that goes there, and then simply the ions that are going to form that are what's on the reactant side. So it's really easy to do once you've identified what the solid is going to be. So kind of leading into that, how do we know what precipitate does form? For instance, how did we know that sodium chloride was aqueous and copper 2 hydroxide was a solid? And the answer is there is a list of solubility rules, which tells us which stuff stays dissolved and which stuff actually will turn into a solid. So to determine a precipitate, you check the possible products against these rules, and that's what's going to be on the next slide. So here we have our 8 solubility rules. Rule 1 applies to group 1A metals and ammonium compounds. They are always soluble. Okay, so just making sure we don't forget what terms mean here. Soluble, means it will dissociate, it comes apart, or dissolved. Okay. Rule 2 applies to acetates and nitrates. Those are all soluble. No exceptions to that. So anytime these ions are part of your compound, that compound will be soluble, and you'll see an example here in a moment, okay, with that. Rule 3 applies to halides, pretty much chlorine, bromine, and iodides. We're not going to worry about fluorides right now, but chlorides, bromides, and iodides, they are generally soluble. Now, there are some exceptions to that, okay? So these ones over here would be insoluble. There's silver. We're not going to worry about mercury because you're not going to see that as anything we do in a lab. But basically, silver and lead are insoluble halide compounds. Sulfates, most sulfates are soluble. The exceptions to that, some of these are 2A, family 2A metals, calcium, strontium, barium. And then you have the same kind of ones as you did right above there, silver and lead. We're not going to worry about mercury all that much. Carbonates, CO3 at -2, if you see that in a compound, that means that those are insoluble. Okay, so if it's insoluble and it's part of your products, that means it is your solid. Okay, that's how we determine which one is the solid. So if you have a product with a carbonate in it, okay, that's probably going to be your precipitate. The only exceptions to this are group 1A carbonates. Okay, so if you have something like, for instance, like Li2CO3, lithium carbonate, that's still going to be soluble because rule 1 up here is going to take precedence over that. It's saying that group 1A compounds are soluble always, 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 always. So it doesn't matter that it's combined with a carbonate as a reactant. Ideally, after they react, then maybe this carbonate will form a precipitate, if that's what we're looking for. Same thing's going to be true here with ammonium compounds. So, phosphates, most phosphates are insoluble. Okay, so they will generally form precipitates, except group 1A metals that are phosphates with them, and ammonium phosphate. So this would be like Na3PO4. That would be soluble. Okay, so remember, like, exceptions to this, right? These would be soluble over here, right? Sulfides, so sulfide ion, most of those are insoluble. Exceptions are 1A metals and ammonium. So if we're seeing like a pattern here of exceptions to the rules for the insoluble part of the rules, they're all basically just referring back to that rule 1 and telling you that one's taking precedence over everything. And most hydroxides are insoluble, okay? And there are a few exceptions here. 1A metals, okay, so like sodium hydroxide is going to be soluble. Calcium hydroxide is actually kind of a mix. It's sort of soluble, sort of not. Strontium, barium, and ammonium. So we're going to use these rules here on the next slide to talk about how to predict which one's going to be the solid. What I would suggest doing is maybe going back a couple minutes here on the slide before, well, maybe even after I write everything down, but I would screenshot this and put it into your iPad, and I'd also make sure you've got these rules down, okay, in your notebook. On a test or quiz coming up in the future, these rules will be a part of a sheet that I'll give you, so, like on the back side of like an ion sheet or something like that. So you don't have to memorize them, but if you don't know how to use them or you're not familiar with them, it's not going to help you very much. So you got to be very, very comfortable using these, and you'll get lots of practice with it today and in the next week or so. Okay, so how do we predict what's going to form? All right, so going back to that example that I was using before with the aqueous sodium hydroxide and the aqueous copper 2 chloride. How do I know what's going to form? Well, what I should do is just treat this first of all as, like, let's just assume this reaction is going to do something. And I've got to change, since it's a double replacement reaction, I'm just going to swap my metals, right? Okay, I'm going to put the sodium where the copper is, put the copper where the sodium is. And we'll change the formulas a little bit here because of the charges on things. So my first option, if I do the copper, it's now mixing with hydroxide. Copper is a +2 charge here being mixed with 2 chloride ions, so that tells us that the formula would be CuOH2. And before I actually go check the solubility rules, we're just going to get the other possible product out there. So that would be sodium ion, which is a +1 charge, and a chloride ion, okay, which is a -1 charge. And then balancing that, right, would look like that. Okay. So the possible products are NaCl and CuOH2. So we want to check these against the rules that we just saw on the previous slide. Looking at the NaCl first, okay, and seeing we haven't yet written what state of matter it is, whether it's aqueous or solid. So checking the NaCl, basically you don't even have to go to Rule 3. You could just go straight to the fact that Rule 1 tells you that all 1A metals are soluble. Always, no exceptions at all. So sodium, right, is a 1A metal. It's in the far left column, okay? Doesn't matter what it's bonded to over here, all right? It's going to be soluble, which means it's going to be aqueous. Okay? So you could check Rule 3, which would tell you most chlorides, bromides, and iodides are also soluble, and that is not an exception with the sodium, so it's both of those are going to be soluble. Okay, we're going to go check the other possible product, CuOH2. There's no guarantee that this is going to be a solid. Sometimes you end up with 2 aqueous products, and we'll talk about that in just a moment. But CuOH2, well, if you go look at your rules, there are no rules for copper ions, right? 1 through 8, there's nothing there on copper. So that means that's not going to factor into our decision, okay? What we need to look at is the other side of this, and that's a hydroxide ion. So Rule 8 says most hydroxides are insoluble, and that's not, the CuOH2 is not on the exception list, so that means it is insoluble, and if it's insoluble, that makes it a solid. Okay, so that's going to be our precipitate here. So that's how we can figure out which one is and which one is not, okay, based on those rules. I do want to talk about one possible situation when you end up with both products being aqueous. So we'll do one more example, and then we'll do one from your homework. Let's say I had this as my reaction, aqueous sodium chloride plus aqueous potassium nitrate. And I go to look at the products. I get NaNO3 plus KCl. And if I go to then check those against the rules, all right, all 1A metals, sodium's a 1A metal according to Rule 1, all 1A metals and those compounds are soluble, always. And there's also a rule on nitrates that says those are always soluble, always. So this compound right here is going to be aqueous. And if we go look at the next one, potassium is also a 1A metal, and chlorides are generally soluble as well, and potassium chloride is not an exception to that. So that is also aqueous. And when we get a situation like this, remember, if it's aqueous, things still exist as ions, right? Everything is just aqueous ions. And if that's the case, well, then what's really going on here is nothing. I have basically a bunch of spectator ions, right? Look at the chlorides. I'll put like a box around those, right? Those are going to cancel. The potassiums are on both sides. They didn't do anything. They're going to cancel. My nitrates are on both sides. Okay, they're going to cancel. Nothing happens. So if you have a reaction like this one, and you go to check the precipitate rules and both the products are aqueous, what you actually have is no reaction. If you mix these two solutions together, nothing's going to happen inside of that test tube or beaker or flask or whatever. It just looks like the two solutions are now one thing. It didn't actually form any solid, so we get no reaction there. So if you do this and you end up with two aqueous products, you don't actually end up with products at all. You end up with nothing. You end up with no reaction. So that is one situation to keep in mind. All right, so make sure you've got that down as an example in your notes as well. Okay, so we're going to look at example number 2 off of the 6.3 worksheet. So, we've got aqueous lead 2 nitrate plus lithium iodide, and if I look at my questions here, it says, what are the possible products of the reaction? So the possible products, well, I could end up with, if I swap my lead and lithium ions, lead's a +2 charge, since it's bonded to 2 nitrates. Iodide's -1, so that formula would be PbI2 plus, okay, and the other possible product, lithium's a +1 and nitrate's a -1, so the other possible product is LiNO3, and if we want to balance that, it should look like that. Okay. So B says, what precipitate forms, if any? So you've got to check the two possible products here. The easy one's the bottom one, actually, because Rule 1 tells you, once again, that all 1A metals are soluble. 1A metals are soluble. Always, no exceptions, ever. So that means that that lithium nitrate is going to be aqueous. Additionally to that, anything that is a nitrate is also always soluble. So that second compound, LiNO3, is going to be aqueous every time. Now, the one above it, PbI2, Rule 3 says that chlorides, bromides, and iodides are soluble, but there are exceptions to this, and that PbI2 is an exception. Well, if it's an exception to being soluble, that would make it insoluble. So PbI2 is actually the solid here. Okay? So, C says, if a precipitate forms, write the balanced net ionic equation. Well, rather than writing out all of the complete ionic equation, I showed you the shortcut, I talked about it a few slides back. How we can do this much more easily than writing every ion out and canceling things is, here's my arrow, my product, if this is aqueous, then that's going to just disappear. The only product then in the net ionic equation is what the solid is. That'll be PbI2. And the only reactants then are the things that make that up. So that would be a iodide ion, which should be aqueous, and I have 2 of those. Okay, and the other ion, which would be a lead +2 ion. I've got 1 of those. So that's the easy part of this, actually. Rather than writing every single ion out, canceling things out, this will do it much quicker. All you got to do is just put the precipitate on the right side and the ions that go into making that on the reactant side. That's it for this lesson.